Before we dive into the topics of nuclear physics in Chapter 29, we have to just take a moment here to establish some vocabulary, some things that I'm sure even the 9th graders have been exposed to some of these words, but those of you taking chemistry, this should be a really good review for you. So we got this notes page about elements and notation, and so when we draw an element of the periodic table, we often draw as a symbol, and then we have the superscript and subscript, so you can get this mass number given by capital A, and atomic number given by capital Z. We're just going to review how to read this and what all these terms mean. So atomic number, capital Z, you should definitely know, that means number of protons. And as we mentioned way back when we first started electrostatics, hopefully you remember, number of protons determines which element it is. So any atom at all that has 6 protons, that's carbon. No matter what else is going on, it's carbon. Anything with 2 protons is helium. That defines which element it is, and that's incredibly important. Now, as long as the thing you're looking at is an atom, it must be electrically neutral, atomic number is also equal to number of electrons, but of course, if there's an imbalance between protons and electrons, it's not an atom, it's an ion, but this is just going to help us as long as we're dealing with neutral objects. And then we get to mass number. This maybe you don't quite know, but mass number, this number that's going to be in the upper left-hand corner, is protons plus neutrons, which means mass number will always be a whole number. Remember, you can't have fractional amounts of protons or fractional amounts of neutrons. They are discrete bits of matter, and so mass number will always be a whole number. We also give the name nucleon to this. So the mass number is the number of nucleons, which is a word that maybe has fallen a little bit out of favor in the chemistry world, but we're going to use it here in physics. It just means particles in the nucleus, nucleon, right? Obviously not accounting for electrons. Now, one of the important things to recognize is this. Like it says on your sheet, mass number is not the mass of the atom. It's something different, and that's kind of the whole point of why we're going to be studying nuclear physics. So we're going to get into all these details. Now, to further confuse the issue, when you look on your periodic table, which is in the back inside cover of your textbook, here is the key to your periodic table. Here is for calcium, the atomic number 20. Don't worry about electron configuration, we're not going to be dealing with that in this course. But here's the atomic mass given as 40.078, and I just got done saying that mass number has to be a whole number, so clearly that's not what this is. This number here is not the mass number. So what is this? Well, if you look below on the periodic table, it tells you the atomic mass values given are averaged over isotopes and the percentages in which they exist in nature. So on the notes page, you're going to read for yourself the next 3 little sections there until you get to the 3 common isotopes of hydrogen. You can pause the video as you do so to absorb the information, refresh your memory if you never, or maybe learn what it means to be an isotope. Okay, so again, the whole idea of isotopes is that we're looking at the same element, but there's different amounts of mass. And since the protons can't change because that would change the element, we're talking about different numbers of neutrons. That's what's described here. So here's hydrogen 1, hydrogen 2, hydrogen 3. These are isotopes of hydrogen. As it tells you here, the number after the name refers to its mass number. So it's always going to be a whole number. Still hydrogen, though. That's why there's always 1 proton here. That's the atomic number. Z is always 1. That identifies it as hydrogen, but the number of neutrons can change to change the mass. Well, they're all still 1 electron because they'll say they're neutral, but here 0 neutrons, 1 neutron, 2 neutrons, that doesn't change the fact that it's hydrogen. Just here it's hydrogen 1, so its mass number is 1. Hydrogen 2, its mass number is 2. Hydrogen 3, its mass number is 3, which is also shown here at the upper left-hand corner. So for example, hydrogen 3 has 3 things in the nucleus. One of them must be a proton, leaving 2 for neutrons. Hydrogen 2, since it's hydrogen, must have 1 proton, but there's 2 things in the nucleus, so the other thing must be a neutron, and here hydrogen 1 is just a proton, just surrounded by an electron with no neutrons in the nucleus. That's really what a hydrogen nucleus is. It's just a single proton. But again, just to make sure we're clear, the number given on the periodic table is a decimal amount. It's an average of all these mass numbers as they have different percentages in nature. So for example, when we look at hydrogen, that mass is given as 1.0079. So this is not a mass number. This is an average of these different isotopes. And clearly, what's the most abundant? Hydrogen 1, 2, or 3? I mean, it's clearly 1. Since this number would just round to 1, that just means that hydrogen 1 is much more abundant in nature than either 2 or 3. In fact, 3, I believe, is not in nature. You actually it's man-made. But the fact is, there is some hydrogen 2 in nature, so it pulls the average a little bit away from 1, but clearly it's almost all 1. Here it is for carbon, 12.011. So you should be able to tell me what's the most abundant isotope of carbon. It's carbon 12. But there's other isotopes as well, 13 and 14, which pull the average a little bit away. So this number here is really just going to tell you, if you were to round it to the nearest whole number, the most abundant isotope. A little more interesting is chlorine, because we can take 35.453. I mean, yes, it rounds to 35, saying there's more chlorine 35 in nature, but clearly there's a lot more of other things. There's a good amount of chlorine 37 as well. pulls the average distinctly away from 35. But just to be very, very clear, these numbers here are really not the numbers that we're interested in. These are averages of all the isotopes. We want to know for a very particular isotope what its mass number is, how many things are in its nucleus. So now, let's get into that. Let's get into nuclear physics. So, one of the overarching themes in all of this atomic nuclear physics is that things are weird, right? All of a sudden, light is acting like a particle, and matter is acting like waves, and it's all strange. It's all very strange. And so here's the strangeness in this topic. When really careful measurements are made of nuclei and the protons and neutrons that make it up, there's always this discrepancy. The mass of a nucleus is always less than the sum of the masses of its constituent particles. So that doesn't make any sense. So to help you visualize what's happening here, let's imagine we're back in normal school and you're all sitting there in front of me in your desks. Now I tell you that I put a scale outside the room, and before you come in the room, you have to step on the scale, and I record your mass, and then you enter the room and you sit down, and I put a giant scale underneath the classroom floor as well, and so then when you're all there in class sitting in your desks, I take the mass of the class as a whole, and I compare the mass of the class as a whole to the individual masses outside, which I've summed together, and I find a discrepancy. That it turns out that your mass altogether as a class inside the room is less than the sum of the masses you had when you were outside the room. And that's what scientists found here as well, that when they add up all the constituent particles, the mass of the protons and neutrons inside, that would eventually form the nucleus, it ends up being more than they were when they were together as a nucleus, and that didn't make any sense. They couldn't figure out why. So with our analogy with you, well, let's say I charge admission at the door. Let's say I have a box outside the door, and to get into the room, to participate in class, you have to put a dollar bill there, which means as you enter the class, you now have a little bit less mass than you did when you were outside the room. That would account for this missing mass. But for protons and neutrons, when they form a nucleus, that's not what's happening. So the question is, what is going on? How do we account for this missing mass? Well, it was Einstein who figured it out with this equation. There it is. The equation you've been waiting all year long to see, E equals mc squared, the most famous equation all of physics. Let's go ahead and box it in, of course box it in, where m is what's known as the rest mass, and E is known as the rest energy. Because obviously if an object is moving, it also has kinetic energy, but when it's at rest, it has this amount of energy because of its mass. Einstein said that mass and energy are really flip sides of the same coin. Mass-energy equivalence. That turns out that mass is really kind of just like energy that's been bundled together and localized, and energy is kind of like mass that's been spread apart, and you can actually transform one into the other. That's really what this equation says, in case you never really knew. E equals mc squared. And so this accounts for the missing mass, that when the particles come together, they release energy, and they actually lose some of their mass as energy. So, while this is the most famous version of the equation, we're actually going to alter it a little bit to the way we're most often going to use it, like this. Delta E, because there's going to be a change of energy, comes from a change in mass. So delta E equals delta m c squared. Box this in a separate equation, where we call delta m this mass defect. Do you all know what a defect is? When something is defective, right? It doesn't work. It's flawed in some ways. That's the idea. There's this flaw. There's this discrepancy in the masses. Some mass has been lost, if you want to think of it that way. Delta E is what's known as the binding energy, that when these particles come together, they are now bound together. And that's the idea with the dollar bill. Let's say, I charge you that dollar bill outside the class, and when you come in, that dollar bill is going to be refundable, but only if you participate in class. So as long as you participate in class and you ask questions and you take your notes, as you leave, I'll refund the dollar to you, in which case you can recover it. But when you're in the class, you are bound together by that missing dollar. That's the idea. These protons and neutrons are bound together by this missing mass. If you then give them that energy back, like giving you the dollars back, then they can disperse. They would be released from each other's grasp. But E equals mc squared says that mass and energy can actually be converted from one into the other. That's the weirdness in this part of the topic. Okay, so let's say we have one atomic mass unit, which I'll remind you is 1.66 times 10 to the negative 27 kilograms, some tiny, tiny bit, the basic bit of matter here, and the basic unit of matter, I should say, and we're going to say that we take this amount of matter and transform it into energy. How much energy will we have? So we can use the equation in its original form, E equals mc squared. We can plug in the mass here, and we're going to use the very specific value of C, 2.9979 times 10 to the 8th meters per second. Go ahead and calculate. Now here we have 5 sig figs, but we only have 3 sig figs in our original measurements, so you can only have 3 sig figs in your answer here, although I guess if you want to carry more, you could. We should be getting 1.49 times 10 to the negative 10th joules. So that's telling you the energy content of one atomic mass unit, which is, pretty small, but we want to put this in terms of the sort of energies we've been dealing with, right? So let's convert this into electron volts. So I'll remind you, here's our conversion factor. 1 electron volt is 1.6 on 10 to the 19th joules. So let's do the conversion factor so we can make comparisons for the other energies we've been doing. We should be getting this, yes, 9.31 times 10 to the 8th electron volts. Great. But that's still, tough to visualize. That's a lot of electron volts. Let's use one of our metric prefixes. Let's put this in mega electron volts. So if you don't know, see if you know, mega, that's millions, or 10 to the 6. So let's put this in mega electron volts. And then, as it turns out, just because of some of the peculiarities of some of the values we're using, maybe they're not as precise as they really need to be, and some rounding issues, the standard for this, and you should be getting something very close to this, but the standard accepted value is 931.5. So we would say that we convert one atomic mass unit, it would be completely disintegrated and transformed to energy of the amount of 931.5 mega electron volts. Now, here I'm writing it as mega electron volts per c squared, which I know looks a little bit weird. Where did that come from? Well, notice I solved this for mass. This is one mass unit, right? So if we take the equation here and solve for m equals E over c squared, which means that energy over c squared is actually a unit of mass, which I know sounds weird, but that works, right? So this is a conversion factor then, which I boxed in as we often do with our conversion factors. So we can do a conversion in problems that one atomic mass unit is equivalent to 931.5 mega electron volts per c squared.